So let's look at this, doing it in 3 separate ways. We'll use the nexthop self command, we'll use the manual nexthop modification, and we'll simply advertise the transit link into the IGP network. Now, advertising the transit link, this is probably the simplest way to solve this problem. We would just go to, let's say, router 2, and under our IGP process, we'll simply advertise that link into IGP. Now, whether I really have a neighbor on that link that I want to establish adjacency with, it's going to depend on the other design issues. So I may want to advertise this, but say the link is passive. Or maybe I want to redistribute this as a connected link. As long as the end result is that the other neighbors have a route to that exit point, it doesn't really matter how they learned it. Technically, they could even learn it through BGP. So one BGP route can recurse to another one, as long as ultimately the route points towards a connected interface. So router 2 could have done the network statement under BGP. That would be fine as well. As long as when we look at the show IP route and match the next hop value, as long as some valid entry comes up here, that's what the ultimate goal is. So now on router 5, if we look at the show IP BGP, we should see that those prefixes learned from router 2, those are now best routes. We see the greater than sign in the show IP BGP output, but notice that the next hop value hasn't changed. Now, if we look at the full route recursion, if we were to look at router 5 and figure out how do we actually get towards that next hop, we could say show IP route to get to 205.90.31.0. Router 5 says this is learned via BGP, and the next hop value is 192.10.28.254. So not ping, show IP route. 192.10.28.254 is reachable via 155.28.0.2. So now we need to do an additional recursive lookup to say how do we get to 155.28.0.2. This says it's connected via our serial interface. This serial interface is running frame relay. It's a multi-point interface, which then means the layer 2 process would need to do a lookup on the mapping. We know what the final next hop is, which is router 2's address. Since we have a frame relay mapping associated with that, now we should be able to send the traffic out that particular link. Now, we could also do the final verification all at once if we were to simply look at the Ceph entry for this. If I said show IP Ceph for 204 or 205.90.31.0, says it's forwarding out serial 0/0/0. So in reality, Ceph is pre-calculating the recursion here and pre-calculating the layer 2 header that's going to be used on that link. If we look at the show IP Ceph detail, we can see exactly the information that it's using here. If we said show IP Ceph internal, this is going to give us even more information about it. Possibly we would have multiple paths to get there. This show IP Ceph internal, this would show us our load distribution information there, where in this case there's only one possible way to get to that particular neighbor. So it says this destination is actually recursive to this next hop, which points at router 2, which eventually points at serial 0/0/0. So as long as we can get to that step where we find the interface, that's ultimately what the routing process is looking for. Now at this point, we are learning the updates from the remote backbone routers, but we're not advertising anything to them. So this means that we have a route to them, but they don't have a route back to us. So if we're going to test the connectivity here, we'd actually have to do some advertisements out to them. So on router 2, I'm going to advertise to BB2 simply a summary of the entire internal address space. Now we are going to come back later and look at the aggregation in more detail. Look at all the specific sub-options that we can do on the aggregate, like the summary only, the suppressed map, the unsuppressed map, and we'll see how that's going to affect the traffic engineering and the best path selection design. But for simplicity here, just to make sure we can test reachability, I'm going to go to router 2, and under the BGP process, generate an aggregate for 155.28.0.0/16. So it's just a classful summary. Now, in order to do this, I need to make sure that I have at least one subnet in the BGP table of the aggregate, which at this point I don't, because we're not advertising anything into BGP. Now, the simple way that I can do this is just to look at the routing table and essentially pick out any of these subnets. Doesn't matter what it is. Could be a connected route, could be a dynamically learned route. As long as one of those subnets are in the BGP table, then it's going to allow me to generate the summary. So let's say this very last prefix, network 155.28.108.0. And that is a /24. Once this particular prefix is in the BGP table, it then means we should be able to generate the aggregate, which is the aggregate here. If we were to then look at the show IP BGP neighbor, BB2's address, and the advertised routes, this is going to show us what we're actually sending to that particular peer. So this says that we're sending them the /24 subnet, plus we're sending them the summary. Now, I don't really care that we're sending them the subnet here. The ultimate goal is just to make sure that they have that summary. The end result of this should be is that router 5 will now be able to reach any of those destinations learned from BGP. So if I ping 205.90.31.1, everyone on the way there has a route to it. Everyone on the way back has a route. If we were to look at the trace for this, as the Ceph table showed us, the route recursion was pointing towards router 2. Then router 2 is directly connected to that destination, which is BB2. But again, when we look at the show IP BGP output, we can immediately tell which of these prefixes are going to have problems with them if they don't have the greater than sign in the leftmost output from show IP BGP. So on router 2, the way that we solved this problem with routing to the next hop was simply to advertise that link into EIGRP, which is a perfectly valid design solution, just depends on what our individual requirements are. If this was within the scope of the lab exam, and the question says don't do that, then we're going to have to look for other possible options. So again, there's only two possible solutions for this. Either we give them a route to the next hop, or we change the next hop so it's something they already do have a route to. This is what we'll look at doing on router 6 and on router 4. Next on router 4, let's look at our configuration under the BGP process. I need to apply this change onto all of these neighbors at the same time, so I'm going to apply it to the peer group. I'll say that when I learn a route from an eBGP neighbor, and I turn around and advertise it to an iBGP neighbor, I want to set the next hop value to my own local peering address. Since my update source for the peer group is my loopback 0, it then would mean all of my BGP routes that are advertised to these neighbors are also going to have the next hop of my loopback 0. Once I make this change, I'm going to need to send a new update out to the neighbors in order to refresh this particular attribute. So the way I can do this is with the automatically enabled route refresh capability. To do this, I'll say clear IP BGP. I want it to affect either all neighbors would be asterisk. I could say 100 for just my internal peers. I could say an individual address. But the key is that I want to send an outbound route refresh. So it's not resetting the TCP session here, it's just sending them a new triggered update. Once I make this change, if I were to go to router 5 and now look at the difference in the show IP BGP, notice that the next hop value for the routes that came from router 4 now has the next hop set to its loopback. And since this loopback is already advertised into my IGP, it implies that for any of these BGP learn destinations, I should be able to perform a final route recursion. And again, the Ceph table is going to show us that. So if I show IP Ceph 118.0.0.0, look at the detail, it says this recurses first to the loopback of 4. Then there's 2 possible ways I could get there. If I look at the internal Ceph entry here, it's now going to show me how I'm actually doing the load distribution, because I have multiple equal cost paths in order to get to the intermediary next hop. So it says to get to this final destination, I really have 2 choices. So this is the final destination. There's 2 interfaces I could go out. In both cases, they're going to router 4, but they're on different physical links. We're doing per session load balancing. There's 2 possible choices. Okay, per session basically means per flow. So by default, Ceph is going to take both the source address and the destination address as the input to the algorithm. It says there's 16 possible choices I have for load balancing. So 16 hash buckets is what Ceph calls it. So it takes the source address, the destination address, puts it through whatever the internal Ceph hashing is, and then it's going to choose one of these buckets. Now, assuming that they equally get chosen 0 all the way through 15, notice how they are spread out. It says the first one goes to the frame relay interface. Next one goes to the point-to-point. Next one goes to the frame relay. Next one goes to the point-to-point. So over and over and over basically means I'm load balancing on a one-to-one basis. But this would be per flow, not necessarily per packet or per destination. So again, the key point about this output is that ultimately Ceph points at a connected interface in order to reach the BGP destination. It means that the full route recursion is correct. We can send it down to the switching path and it's not going to have a problem moving the packet between the interfaces. If I look at the show IP BGP 118.0.0.0, since I did not yet update the next hop value on router 6, it says the path I'm learning from router 6 is still invalid because the next hop is inaccessible. So if the next hop value is not reachable, it means I will not consider that individual path for best path selection, even if the local preference value was higher than the first one, or if the weighting value was higher, or the metric value was lower. As long as this next hop stays inaccessible, then it means I'm never going to consider this particular path for best path selection. So we saw how we could change this on router 4 was with the next hop self command under the BGP process. So that's a perfectly valid option. It says that for any routes that are coming from my eBGP peers, which in this case it's just this one particular neighbor here. For any routes that come from the eBGP peers, then when I'm sending the routes to my iBGP peers, I'm going to change the next hop value so that it's my own local loopback 0. Again, the reason why we're using the loopback 0 because that's what the update source is. If my update source was fast Ethernet 0/0, that's what the next hop value would be changed to. Now on router 6, we're essentially going to do the same thing, modifying the next hop, except we're going to do it manually. And we'll do this with a route map that says to change the next hop. Under the route map, I'll say set IP next hop, then whatever address that we want to send this to. Now, I could use an address that is connected to router 6, or I could technically do whatever I want. I could say 1.2.3.4. Now, if the other neighbors don't have a route to 1.2.3.4, then that's going to be a problem. But anything that they essentially can do the full route recursion on, that's what we're ultimately looking for. So this could be my loopback. This could be my Ethernet interface. The only disadvantage of using the physical link would be what? If router 6 were to tell all of its iBGP peers that the next hop for these eBGP updates was this interface, what else is that going to impact in the design? It would mean that if router 6 loses its connection to that segment, then the BGP peers would not be able to use any of those routes. Now, it could be possible that that's actually what we wanted for the design. So maybe on router 6, this should be the only possible exit point. And if this link is down, we don't want to reroute over that interface. In which case, that would be valid to set the next hop to this interface. Really depends on how we're trying to affect the traffic flow. Now, another valid case to do this would be if you're trying to do some sort of enhanced object tracking with the IP SLA agreement. I could say, for example, that I want router 6 to advertise the BGP updates, but only if some attribute is true about the connection to BB1. So maybe if the delay is less than some value, or if I'm able to reach my DNS server via that exit point. Okay, I could do whatever application check that I want. Then that IP SLA instance, I could tie this to a static route that is advertised into IGP. Then router 6 could set the next hop value to that under the route map. So by using the route map, it's going to give us more flexibility as to whether we should actually use that particular exit point or not. So let's take a look at a quick example of this. Let's say on router 6 that I want it to be used as a BGP exit point, but only if I can guarantee that the end-to-end connection to BB1 is actually up. The potential problem I could have is that if I look at the show IP interface brief on router 6, I'm using the main interface for frame relay. The main interface for frame relay, remember, is going to use what to figure out if the line protocol status should be up. It's going to use the LMI keep alive from the frame relay switch. Now, it's not going to use the status of the DELC, and that's what the issue is going to be. As long as router 6, when it looks at the show frame relay LMI, as long as we are receiving these status replies, then the link is going to stay up. Even if the frame relay PVC were to go down, it's not going to change the status of the interface. So this means that if BB1 loses its connection, then router 6 is not going to know about that. Okay, it knows that the circuit is going to go down, but it's not going to affect the physical link. So what I'm going to do now instead is create an IP SLA instance that says I'm going to send an ICMP echo to 54.28.1.254, and I'm going to send this every 5 seconds, and my timeout is 2,000 milliseconds. So basically every 5 seconds, router 6 is just going to say ping this address. We can see right now it's getting a response. Next thing I'm going to do is tie this SLA instance to an enhanced object. I'll say tracked object number 2 is checking against an IP SLA instance number 1. If SLA instance 1 is up, it would mean that the tracked object is up. Now let's start the SLA instance. We'll say IP SLA 1 or IP SLA schedule 1. Start now. The lifetime is forever. So I'm going to start the ping, and it's going to keep going indefinitely. We can see this also immediately changes the state of the object to be up, because right now the pings are working. Next step is that I'm going to create a static route that points to null 0 that I'm essentially just using as a placeholder. So we'll use any random address. Let's say 169.254.0.1/24 or /32 goes to null 0, but I'm tracking object number 2 with this. So this is any invalid address, basically. 169.254 is the link local address space in IPv4. So this would not be globally routable in the public BGP table. Next thing I'm going to do is under the EIGRP process, I'm going to redistribute this static route. And I'll set whatever metric value that I want. Let's say 100 megabits per second, 1,000 microseconds of delay, or actually 100 tens of microseconds, a reliability of 255, a load of 1, and an MTU of 1500. Okay, it really doesn't matter what the metric is, because I'm the only possible exit point for this static route. So now if I were to look at any other router in the IGP network, let's say I were to go to router 5 and say show IP route 169.254.0.1. Router 5 does have a route to that. This means that the tracked object is up. Now I can't actually ping this address because this is going to router 6's null 0. That's not really the point of it. The point of it is just that it's a placeholder that I'm using to combine with the IP SLA instance. So as long as this route is in the routing table, it basically means that my connection to BB1 is up. Now I could take this logic even a step further and go to router 6 and say when I advertise my BGP updates out, I'm going to change the next hop value so that it actually points to this placeholder route. So if we show run or do show route map, okay, I said the route map's name was change next hop, where I'm going to set the IP next hop to 169.254.0.1. Now under the BGP process, I'll say when I send updates out to my neighbor, that is the peer group. So if I show run section router BGP, we'll say neighbor iBGP peers. I have the route map that is change the next hop outbound. Then lastly, router 6 needs to apply the new policy. So we'll say clear IP BGP star outbound. This is going to send a new update out to them that should ideally update the next hop. So now if I look at router 5, let's look at the show IP BGP. We see the next hop value was changed to that 169 address. So now let's look at what's the end result of this. Let's say that from switch 4, I'm going to trace 112.0.0.1. Notice right now that this exit point is router 6 out of our network. So from switch 4's perspective, the packets are going to switch 2, to router 5. From router 5, we have a couple different choices. Router 5 in this case is sending it to 1. 1 is then sending it to 6, and then 6 is sending the packet out. If I were now to go to BB1, and let's just say the router crashes. Okay, so we'll reload it. From router 6, this means that the tracked object is going to go down, which then means that even if we were to continue to advertise the BGP route, router 5, or basically anyone else in the topology, they would no longer have the route to the next hop, which then in turn means that the route recursion would not complete and the BGP route could not be used. So the key behind this is that there's other ways to base the convergence of the BGP routes than the actual BGP hello and hold time. Because when we look at the default timers, let's say we go to router 4 and say show IP BGP neighbor 204.12.28.254, it says the hold time for this is 3 minutes. So for some reason that connection goes down, I may not notice this for 3 minutes, which potentially could be tons and tons of traffic that's getting dropped. So by tying this to some feature that can do much faster convergence, or do convergence based on application level intelligence, then it gives us more flexibility as to how we're actually controlling how the traffic leaves the network. So the key point being here is that BGP gives us a lot of flexibility to do this. We'll see later when we get into more details about the best path selection and doing aggregation, there's probably 1,000 different ways to solve the same problem in BGP. Just there's many different options that we have available to us. And again, within the scope of the CCI lab exam, the key is to understand what are all the possible options. So then it really doesn't matter what the question is asking. If the question says don't do A, B, and C, that's fine because I know that there's ways D, E, and F that I could solve the same problem with. And a lot of times that's going to be the difference between getting the section right or getting the section wrong. If they could be asking you something that you just think is impossible because you didn't know that that was even an option to begin with. So if we look at our final configuration on router 6 here, and let me put this into Notepad so we can see the whole thing all at once. So first we have the IPSLA instance. Which is this. Okay, so we're doing the pings. Then we have the object that is tracking the SLA. The object is then referenced from the access list, or not the access list, the static route. Then we are changing the next hop to that particular address. Okay, so the full way to read this config, it says ping BB1. Ping them every 5 seconds. If I don't get a response back within 2 seconds, I'm going to consider that they're down. If they are down, it's going to cause object 2 to go down, which is going to cause this static route to be removed from the routing table. Since this address is the next hop of the BGP routes, it means that anyone who learned the prefixes from me now says that I'm an invalid path in order to get to those destinations. Because if they don't have the route to the next hop, it means that they're not going to consider my path for best path selection. So it's kind of a roundabout way to get the network to reconverge. But the advantage of this is that we could define whatever we want in the SLA. So I could say that maybe the service provider has guaranteed me 100 milliseconds end-to-end delay because that's where my voice over IP traffic is going. So if my delay goes up to 200 milliseconds, maybe that's unacceptable for whatever application that I'm using. Then based on that, I could force router 6 to withdraw the routes from the BGP table. So we'll see some other advanced examples of this when we get to other features in BGP. But again, the ultimate goal here is that since BGP was designed to be a policy protocol, we have a lot of flexibility as to how we can solve these different design problems.